Hi, we are here to tell you about the latest expedition to the secret bunker. I'd like to draw your attention to the timestamp that we put on this version of the slide deck. It's been through quite a few changes since we started.
Not all of which were recorded.
True. So we spent a number of weeks doing some experimentation with version 12 and the table reorg utility. So the secret bunker has a history. We started, the first one was in 2002, and we started with figuring out how best to run progress on Linux and what kind of performance you could expect and that kind of stuff. So here's the first three secret bunker participants: myself, John Harlow, and Dan Foreman. And this is the secret bunker location. Here's our benchmark laboratory, which was John's garage. We had another table in there later, so we had a little bit more equipment than what you see in this picture, including the bicycle. Now this year, here's the instructions for how to get to the secret bunker. Here's a photograph of the secret bunker.
Nearby.
Yeah. So, topic for this year is using the table reorg utility to do the equivalent of dumping and loading. There's several other ways to do dumps and loads. So since the table reorg utility is brand new, we figured, let's see how well it works and what it does. So that's what we focused on. This is our test machine. It's a Dell PowerEdge from about 2009, which I bought off eBay some years ago. It's got two processors, 6 SATA disk drives, and 64 gigabytes of RAM. You can see here what all of the components cost that we bought. So the computer itself was $189, and then I had to buy some other stuff to make it usable. It came with one small disk drive, not useful for us. Anyway, so $600 US in total for this machine, which is now 14 years old. It's a pretty stout box, even by today's standards. The BI grow test time is 1.1 seconds, which is quite fast. It's not as fast as you would get with SSD M.2 disk drives or storage plates, but it's pretty fast for rotating iron.
It's faster than most of the machines I've seen in my consulting days, that's for sure.
Now, we weren't focused on performance on this particular go-around of the bunker tests. So, yeah, it's a fast machine. We could have used a slower one. Would have been okay for what we were trying to do, which was to learn about table reorg.
Okay, my turn. So why, I think I am on. Hello? Why do you care about table reorg, dump and load? This should be review for many. Am I pressing this one?
Yeah.
So fragmentation, there's 3 forms of it. In the talk I did yesterday with zero downtime, we had record fragmentation. because it's actually pretty difficult to get physical scatter or logical scatter. You have to work hard at it, but you can get record fragmentation fairly easily just by creating records, then coming back and updating the records and making them large enough that you know they're not going to fit in the same block. So that's what this diagram shows here is the first kind of fragmentation, which is record fragmentation. So you have a block that has a record header in block 1, then block 2, block 3. When the database sends that back to the 4GL, it concatenates them all together and makes the full record. But when they're stored on disk, they're in 3 different blocks. So that means there's 3 different reads that need to be done to just go fetch that one record.
So one comment about that is this kind of fragmentation happens for 2 reasons. One is the record's bigger than a block, so you need to break it up into pieces to store it. And the other is because you have some amount of free space in blocks, but not enough to hold the whole record, so you might have to break it up. Even though it might fit in a block, you might have to break it up to get it to fit in the space that's available.
Second time is physical scatter. This is a comparison of type 1 storage, which hopefully nobody's using anymore, but you can see if each one of these colors represents a row from a different table. In type 1 storage, they're all intermingled in different blocks or same blocks, and then they all get messed up and jumbled together. So when you're trying to read 7 rows from the customer table, you might have to read 7 different blocks. But if you dump and load, after the dump and load, it looks like the bottom. So assume that the red blocks over here, or the red records are all on the customer table, and you want to go read 7 red records, the chances of you getting the 7 red records in one block read is much higher in the bottom scenario than it would be in the top scenario. But this is type 1 storage, and you don't get physical scatter that much in type 2. You still can, but it's not really common.
It's reduced quite a bit compared to type 1, and nobody should be using type 1 storage anymore.
Right. And the third I learned from Tom, logical scatter. This is how ordered are they when you're looking up via an index. So the rows could all be back in this good form, but they still might not be in the order that you want. So what's your most used index that you're reading against, and what order do they show up? So here we are in a type 2 storage area, and they're all, blocks are all, the records are all right near each other. There's no physical scatter at all, but yet when I want to go find those 6 customer records, I still have to go read 6 blocks because they're not in order for that index, and that's logical scatter.
Yeah, one comment about that is the records can be in only one place at a time. So the physical storage order can only match one index. So you have to decide what index do you want to use.
Right, so knowing your most used index is important. By default, all the utilities dump by the primary index. And that tends to work pretty good because hopefully when people design the database, they believe the primary index is the index that's most used. Not always the case.
Well, there's usually a big time lag between today and when the database was designed.
Right. So you may find out that the primary index is not the most used index, and in that case, all the utilities provide you a mechanism to be able to dump the data out in the index order that you want. So you can specify the index that you want to do the dump. So what is table reorg? It's new. It's in 12.3. So it's not in a long-term release yet. So it's probably not in a lot of people's hands, or people haven't tried it much. 12.8 will be the first long-term release that has table reorg in it. So it's an online utility that puts rows in physical order that match the index. It's either going to use the primary index, or you can specify the index that you want, and it runs online. So it operates on part of a table, and it will remove all the fragmentation that we talked about. It'll remove the record fragmentation, where a record is split across multiple blocks, if it can. The if it can is if the record's larger than a block, it's going to be split no matter what. But if the record is smaller than a block, it should be able to remove that fragmentation. It will remove physical fragmentation because it'll get things in order, and it'll get things in order logically the way you want the data ordered by your most used index. Let's tell us more about this, Tom.
It's my turn.
Yes.
Okay, so in a type 2 data area, you have your blocks organized into what are called clusters. So what you see here is 4 different clusters. If I count correctly, those clusters have 64 blocks each in them. And so from a database space allocation perspective, you allocate a cluster at a time rather than doing a block at a time like you would in later releases. And all the data in a type 2 data area in the blocks in the type 2 area come from the same table. So you don't have orders and order lines and customers mixed together. You only have the data for that one particular table in that area. For indexes, it's that way, whether it's a type 1 or a type 2 area. After you delete some data, you're going to have holes, because if you delete enough data to empty out the block, then there's a block with nothing in it. Or if we were looking at records here instead of
Sorry. I knew that was
So, you can look at these pictures a couple different ways. That could be a block with a bunch of records in it, or it could be a cluster with a bunch of blocks in it. But either way, when you delete data, you end up with holes. And so eventually you have this kind of Swiss cheese of a storage area, and that's part of why you want to do some of this reorganization work, is to consolidate that.
Yeah, however, within a block, you only have one hole because the records get squished to the bottom, so the holes get closed up and all the free space is contiguous.
So after you've deleted a bunch of records, the RM chain is a list of the blocks that have usable space. So when you're creating new records, you're going to look on the RM chain for some space, or when you're needing to expand a record, you're going to look for some space on the RM chain. And it's going to try to reuse those holes, but that means that things are going to be disordered. They're going to be scattered around much more than they were when you originally loaded the data, or when you created it from scratch, or however you built your database the first time. And so these numbers are kind of the ordering of the RM chain, which again is scattered all over the place. When you add new stuff, the new stuff goes wherever there's room for it, not necessarily in sequential order, but wherever it can find enough room, kind of sequential, hopefully, but logically sequential, not physically sequential.
We had a notion at one time of having a type of table organization where we would always put new records at the end. So you'd always add on at the end, which was handy when you're doing things like you're keeping records that are ordered by time and deleting the early records when you don't need them anymore. But that hasn't been implemented yet.
Is that in the product plan somewhere?
How does he know?
It's in my product plan.
I was just checking. Maybe it's been there for a long time.
That's right.
There's a whole lot of stuff that's been done lately that had been in the queue for a long time.
That's right.
So when you do a table reorg, what you're going to do is you're going to move things around to establish a new physical ordering. So we're going to take things from wherever they were, like the first couple of blocks there, and we're going to move them. Well, okay, no, these are blocks, not clusters.
These are records now.
Yeah, now we're talking about records. So
I was lazy.
So you take the first couple of records and you put them in this new block that you've allocated over here, and you basically go through that iteratively, moving things one at a time into the new space. As you fill up the new space, you empty out the old space. I think that's what the next one is going to show us. Right, so we start filling them up, and then the first one empties out. So there's this process of moving things from a broken up, scattered approach into something that is much more ordered over here on the right-hand side.
Yeah, one thing that's slightly misleading about this diagram, though, is you're not pulling records from those first cluster and emptying that out and then moving on to the next one. You're going by index order. So you might pull a record from the first cluster and one from the last, depending on where the index takes you.
True.
You will have a little bit of database growth doing this.
We will
see.
discuss database growth.
We have results.
Yes.
We have data.
And obviously, when you move the record, what's going to happen to the rec ID? That's right. It's going to change. So that's something to be aware of, particularly if you're using rec IDs for some ungodly reason. And the clusters eventually get reused as you move to the right. You're going to start reusing the space in that cluster that you just emptied out eventually. And when you're done, there's no holes in the blocks, and things are compacted as compactly as they can be for the data that you've got. Now, obviously, there's going to be a little bit left over at the very end, but all of the intermediate blocks will be filled and packed together in a fairly optimal manner.
Or an approximately optimal manner.
Back to Gus. You're next, Gus.
All right, so that's all theory.
Right.
Let's do some experiments now and see what happens. So here's a list of the various things that we've done. So we started with a copy of the ATM database. We made several different variations of that in different sizes, because there's one huge table in that database, the account table. So we tried it with different sizes just to see how size and performance were related, and also database size changes. And then we did some experiments where we fiddled with the records. So the first few in the list here, we create a database, don't touch it, and then we run table reorg on it to see what happens. So it's a clean database to start with. And then we go into more interesting stuff. So the first experiment, we start with 10 million account records, relatively small database with about 1.5 gigs. And to start with, there's no fragmented records. The records are about 120 bytes, roughly. They're not all exactly the same size, but that's the size mostly. The RM space is almost all used. It's 94% used. So it's a fresh database that's nice and clean. And then we run table reorg. So table reorg goes pretty fast. Took 6 minutes and 57 seconds in this case. However, the database doubled in size. But in the end, there were still no fragmented records. And the RM space was now 60% used, which I find a bit strange. But there's a reason for that.
One thing we don't talk about, but we use this Rex 1000. The default is Rex 100. What that means is each transaction would have 100 records being moved, and then that would end that transaction. So we did Rex 1000, thinking it would be faster, and it may or may not be. We'll see later. But what it does do is, for every transaction that it does, it writes to the screen. So you can imagine if you have many, many rows, you're going to have many, many lines written to the screen telling you what's going on every 100 records.
There is an option to turn that off, though.
I didn't see that, but keep going.
Okay.
Well,
But you can just shut those messages off so they don't get generated. So we have 60% space utilization. Why is that happening? Well, the database grew, and now we have lots more record blocks, some of which are now empty because we moved all the records. So we added more space and then moved all the records, and they're all stuck together nice and clean, but we have all those record blocks where the records used to be that are now empty. So that's why the space utilization is less. Then I ran the same thing again. And I'm thinking, okay, I just did a table reorg. It's all nice and fresh, clean stuff. So if I run table reorg again, it's not going to do anything. Well, guess what? I was wrong about that.
Well, you ran it, so it says I got to do something.
That's right. So now we got, again, some more database growth, but not doubled. And again, no fragmentation, no free clusters. And space utilization is now 62% instead of 60, so it's about the same. So we've run the table reorg again. It hasn't really accomplished anything. Okay, on to the next experiment. So now we make a database that's bigger. So now we have 1 billion records. So the database is 14 gigs. No, was it 1 billion? No, in this one it was actually 100,000.
Right.
So it's 10 times as many records as in the first experiment.
I see version 19 coming.
Yeah. I have to fix that, yeah. So now we get a 14 gig database, and we do the same thing. The only difference is the database is bigger. So this time, it takes a bit longer, 72 seconds instead of 7 seconds.
72 minutes.
Yeah, 72 minutes, right. Which is quite a bit longer. It's more than 10 times, but 10 times as many records. So it's not linear. And you'll see in the next experiment an even longer time. So now the database grows from 14 gigs to 22 gigs, not doubled, but still a significant growth. And then 60% space utilization. So the RM chain now has a lot of records, a lot of blocks on it. So again, we haven't really accomplished anything except made the database bigger and the RM chain longer. But there's no fragmentation. Now, as I mentioned earlier, these records are small, so there's not much opportunity for fragmentation either. Okay, then run table reorg again without touching the database between when the first table reorg ended and we do it again. About the same amount of time, roughly. Not much database growth. So now we end up with even more blocks on the RM chain. And that's something I'm curious about because I don't know why that happens. Because here we've expanded the database a little bit, but not enough to explain why there's twice as many blocks on the RM chain. So I don't know why that happens. So run it a third time. This time, nothing happened. We got 16 more blocks on the RM chain, which is insignificant. But the database didn't change size. The space utilization didn't change. So the third time, it behaved as I would have expected it to do the first time. Again, I can't explain that. I don't have enough experience with this utility.
But it took the same time.
What?
The first iteration, it took same time. Something was written, maybe nothing was written at all.
Oh, it moved.
Yeah,
It moved records.
they got moved,
It's just moved them more efficiently.
right.
So it found the space to reuse better this time.
Yeah.
And which DLC was this?
12.7. Ran.
Just two replications for my, and
Where are the indexes?
The indexes are in a separate area.
And there's one index.
Yeah, so in this table, there's one index, and the table is in an area by itself. And the index is in an area by itself as well.
Okay, you're up.
That must be why I have the microphone. So the first scenario, we're using, as Gus said over and over and over, records that don't have much fragmentation in them to start with, and are all very similar in size. So we wanted to make a database where it's a little bit more realistic. We varied the record size from between 100 to 500 bytes and made every 20th or so record randomly really big, which resulted in a database much bigger than the earlier one, and put a lot of blocks on the RM chain. And now we have almost 200 million fragments rather than just the same number of fragments as you have records, so there's no fragments. So in this case, we're pretty highly fragmented. This is almost 100% fragmented, right?
Yeah, one thing to note about this database is it was created the way the ATM database is normally built with 122 byte records. And then all those records got updated to change the length.
Yeah. So we're going to have something more like that multicolored organization that Mike was showing earlier in terms of record sizes and fragments and that kind of fun stuff. So we do the reorg again. This time it goes 86 minutes, 35 seconds. Sounds to me like it had a lot more work to do. The database grows from 37 gig to 53 gig. And the number of blocks obviously increases in a very similar fashion. And the fragmentation goes away. 71% RM space utilization, and the RM chain has grown tremendously again.
Okay, so we are, so far we've done experiments on things that are not fragmented to see what happens. Then we did record fragmentation to see what happens, and this could be life for you guys. You know, record fragmentation, run DB analysis. If you've got 20% fragmented records, if your fragmentation factor is 1.2, that's significant. You should be doing something, and this could be the solution. But now, a common thing, well, it wasn't really that common, but was what if you do a purge? So we created two scenarios. This scenario here is we create account records, and we wanted to have 500 million account records, so we created 500 million account records normally, and then we created 500 million account records that had a negative number. So you'd have 1, then -1, 2, then -2 in this scenario. And then in this scenario, we then deleted the negative numbers. So what you have are interleaved empty space in each block. So you'd have record 1, then you'd have some empty space. Record 2, then some empty space. So each block now has empty space associated with it because we deleted interleaved records. So you can see what it looks like there. 1 empty, 2 empty, 3 empty, and then a total 500 million records. Then we created another scenario, and this scenario was using the same concept of positive numbers for the account ID was what we cared about, and then we created negative numbers as well, but they were all contiguous. So this was built putting the negative numbers in first, and then after that, running it normally to put positive numbers in. So this would be more like a audit table or a history table, and you did a purging out data from 2020. So you're deleting all the data from 2020, and you're leaving data from 2021 to current. So when we deleted the the negative numbers, what we ended up having is a whole bunch of empty space in front, and then you had your account records that started with 1, 2, 3, up to 500 million. Make sense? So these are two scenarios. We're going to be talking about these for a while, because I think these are the two that when you do a big purge, this is the time to think about doing a dump and load. So the next question is, Tom, how do you efficiently delete 500 million records?
One at a time.
Here you go. Because it didn't seem that way.
For each account, delete account, end. 500 million individual transactions. That sounds like a bad thing, right? And we've all gone to the K-base and we found code that looks similar to this.
Well, that is cut and paste from the K-base.
There's probably 3 or 4 of these. But anyway, where you have an outer loop and you have a transaction and you do them in chunks. And typically updates you're going to want to do like this because you get a bigger chunk of work done. You have less activity on the BI file. It's more efficient if you're just doing an update. Unfortunately, the K-base is somewhat inaccurate in that this is not a good way to delete data. Because the theory behind that is instead of 500 million transactions, you go down to 50,000 transactions. And it works really good until it doesn't. Basically, you're deleting data and you're causing index entry placeholders to be put in place. And eventually, as you go through it, it starts taking longer and longer and longer to get to the next record that you want to delete. And that's the part where it worked good until it didn't. So this is like if you ever had that experience where something starts out really fast and then it gets slow and it gets slower and slower and slower.
And then you think, oh, it's completely stopped.
Yeah.
But
But actually it's doing work in the background.
So I did this, and I wasn't really watching it because I had counters and stuff, and I was looking at this, going, "Wow, it's just not giving me any feedback anymore." So I went in Promon, and I'm looking at Promon, and it's reading database records like there's nothing else on earth, right? It's just completely reading database records and no other activity, because it's trying to find all the deleted placeholders. Well, not trying to. It's just skipping over them.
So there's a talk later today, at the end of the day, from Patrice and Dr. Paul Magru's. I hope I pronounced that somewhat closely. The curse of deleted key placeholders, which will go into this in a lot more detail. Rob?
Mike, you just said it was reading records like there's no tomorrow.
Reading database blocks like there were no tomorrow.
Yeah, it was actually reading index blocks.
Right. So it was just completely reading index blocks.
So actually, for each account, delete account, end works best.
Am I going to get I told you so?
I was going to spare you, but I told you so. So, yeah. So the difference is 50,000 for eaches versus one for each that just does it all at once.
Yeah, go back to me.
So why does this work better?
Because it's not going back through the index.
Right. Was you asking them?
Yeah.
I always try to answer Gus's questions, always.
All right, well, the answer is because when you're doing the 50,000 transactions, you're doing 50,000 new for eaches, and each for each, when it starts, it's got to figure out the right cursor position.
It's got to find the beginning.
And if you do it as a single transaction, it can just next, 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 and there's no skipping over the index placeholders, which are still there, you're just not skipping over them because you're going
Right, so
next.
another way to say that is for each time you start a for each, it's got to find the beginning. And when you did it the first time, the beginning was right at the beginning of the index. As we started deleting, it couldn't, all we had were index blocks that had completely filled with index delete placeholders, and it wasn't the beginning. So it had to keep reading every index block to find the beginning, to find the first record that it could go after. So that's why it was a surprise, but not a surprise once it happened.
But aren't they cached?
What's that?
But aren't they cached?
Not really. Okay, so back to, now that we deleted the records, what happened here? So taking table reorg with all the defaults, it took 10 hours and 52 minutes to complete. And we're doing the interleaved ones. So this is the one where we had record 1, ID 1, then ID negative 1, ID 2, ID negative 2, and then we deleted all the negatives. So now we have gaps in every single block.
Yeah, so every other record got deleted.
Right. So then I thought, well, the default is 100 records per transaction, and I'm getting a bazillion lines out to an output file. Maybe the output file is causing this to have a problem, or just writing to the screen. So I changed the transaction scope to be 1,000 records, and it saved a little bit of time, but not as much as I thought. So we went from 10 hours, 52 minutes to 10 hours, 40 minutes to complete. The database size grew, as we had talked earlier. It was going to grow. It grew from 126 gigabytes to 171. So why is that? So I did a lot of investigation on this because I didn't think it was going to grow. I thought that the process would have started at the front, and it knew it had holes. So just think about this. If you can fit 64 rows per block, and you've taken 32 rows out of that block, once you start moving half a cluster, or that full cluster, that cluster is going to be completely free and be able to be reused as you're working through the next cluster. And that's not what happened. So doing the math here, 500 million records, average size 124 bytes. The database block size in this case was 8,192. How many records fit in a block? This is an important thing to figure out to get your records per block right. And you do the math. A database block is about 8,000 bytes because there's some overhead at the top. So you do the math, and you should be able to fit 64 records per block. So how big was the freshly loaded database? So a freshly loaded database has an account area of exactly the 65 or 64 gigabytes-ish, right? So the 65 million or billion, 7,512 kilobytes or bytes. There's 512 8K blocks per cluster, which means that this held 15,499 clusters. This is just doing math, right, to figure this out. The database prior to a table reorg had an accounts area of 130,000 bytes. So it's much more because this is the one that was not freshly loaded. So this is the one that has the interleaved gaps in them. So that had 31,000 clusters doing the same math, 31,003. After the table reorg, the account area grew, still the same math. It grew to 42,466 clusters, which is an additional 11,463 clusters. Not how I thought this was going to work. When you look at the slides that we had in theory, you would think you would add 2 clusters, 4 clusters maybe, and the process would just be able to keep up, moving through the clusters and filling up behind it and, having some gaps. So it was unclear to us why it grew 11,463. When I looked at the RM chain with this, which was huge, as you can imagine, it started out at the 9 million spot, and it went for a long time, and then it went to 1. So it started somewhere, and then it seemed like it finally figured out wow, cluster 1 is empty. And it was like about halfway through the process that it figured out cluster 1 was empty. So then it started at cluster 1 and started filling from cluster 1, 2, 3, 4, 5. This is your quiz.
Yeah. So the quiz is, why are there 11,000 some additional clusters now?
I'm not going to answer.
I'm not going to answer either because I don't know.
Right?
I thought it was theory.
Oh, you have a theory?
I have a theory.
I have a theory also, but I don't know anything for certain.
What's your theory?
I think it has something to do with the create and toss limits, and that the RM chain that was there from when you built the ATM didn't have free space, and so it had to go through that whole process you were talking about of finding the part of the RM chain that had space.
Well,
That's my
remember that this is the database where every other record got deleted, so there's plenty of free space because
But
we deleted half of the records.
But there was an RM chain there to start with.
That's right.
And that RM chain is at the front. So you have to get all the way through that before you get to the parts of it where you're going to find the space. That's my theory.
That's a pretty good theory.
No, but your first set of RM blocks, because you had a database where you had deleted half the records, one, like every second record, right?
Right.
Yeah.
This is interleave deletes, yep.
Yeah, so the free space should be evenly distributed throughout the whole.
Right, but when you table reorg, you're not necessarily emptying, you're emptying all over the place, so you're not really freeing up clusters, right?
This is ATM database built so things are ordered. So block 1 is going to have record 1, record -1, record 2, record -2, record 3, record -3, up to 64. And so there's only one index, so it's only going by that one index.
Okay, so you have 64 records per block, you've deleted 32 records for the first block.
Yep.
So that block previously wasn't on the RM chain and now should be, right?
Well, we don't know if it was on the RM chain or not.
It probably was on the RM chain from deleting half the records.
If it was logically full and probably close to physically full, but it wouldn't have been, right?
Correct. So when the database was built, there should have been not much on the RM chain. When you delete the negative numbers, so now you're deleting half the records in each block, those blocks will definitely be on the RM chain.
But the question is, at which end?
Well, so record number 1 goes on the RM chain, then it's followed by number 2, then,
right.
so it's in backwards order.
When a new block goes on the RM chain, does it go to the front or the back of the RM chain?
It could go either.
Because then that would explain it if you inserted blocks on the RM chain at the front, then now the first block that you're deleting is actually 20,000 blocks deep into the RM chain if you're inserting RM blocks to the front of the chain. So you're looking at the blocks that you're going to move last at the front of the RM chain. And that's why you had that.
So here's,
Before you had that, all those records down the RM chain. Once you finally got to the end of that, then you started seeing your unused blocks.
so
Yeah, well, except that the RM chain searches are bounded. You don't go all the way down to the end.
And I think that could explain the growth. If it gives up because it never found a usable block, it would say, I have to allocate more space and put that on the front of the RM chain.
Yeah,
which
32 blocks at a time off the RM chain, right? Or rec search depth, whatever it's called. Rec space search depth.
Yeah, so this is all good, but I am going to tell you my point of view on this. If this table reorg is going to be using RM space that may not be ordered, what's the value of the tool? Because you now have holes, and now we're going to go and try to use table reorg to get rid of the holes, but we want them in order by the index, but it's going to be using the RM chain, which could be in the picture all over the place. The rows are not going to be in sequential order by the index.
except we don't know what table reorg really does.
Right.
So we don't know if it's using the RM chain or not.
I certainly hope it's not, because that certainly would defeat the whole point of it.
Yeah, so we have theories, but no evidence.
Right.
or no conclusive evidence. So eventually we'll find out.
Or not. Okay, so we have two problems that were discovered during this. Obviously, we talked about the area growth for a while. All the slides talked about the area growth. The database grew. We don't really understand why the database grew, but there was another thing that happened. When I ran this and it was running, it sat for 2 hours not doing anything. It was reading database blocks, but it did not do anything at all for a 2-hour period, which here's a situation, right? So this tool is a restartable tool. The point of it being restartable is to have it run during off-hour times. So you probably don't want to run this during the day when things are busy. You probably want to run it over the weekend or at night on a periodic basis. But if it has a 2-hour startup time, just to go figure out before it does absolutely anything, that's a pretty significant impediment to doing things in chunks overnight. So we had to go figure that out. But before we do that, let's go to scenario 4. And Gus, we're back to you.
All right, so in this experiment, we've modified the database so that we have a big chunk of free space before the records start. And then we do a table reorg on that. And again, here we have a pretty large database. So let's see what happens.
Well, before you go there, go back to the slide.
Yeah.
So it took 7 hours compared to the 10 hours. So it took 7 hours compared to the 10 hours, and the database didn't grow in this case.
Yeah.
I think that's the point here, right? So,
Right, so nothing really happened,
well,
except something did.
this worked the way I think we all expected it to work. That it starts freeing clusters, and it starts moving data. So it adds a cluster at the end, starts pushing data to the end, freeing clusters at the front, and starts filling from the front. So things are now really ordered. The database size did not change because it had all that free space and knew where all that free space was, and it started using it. So this one, in my mind, worked the way I expected it to work, where all the other examples did not work the way I expected it to work.
Yeah, and in this case, the data size was significantly bigger than in any of the earlier ones.
Did you just add an extent with free space to the database to have it pre-allocated?
Can you say that again?
Did you add an extent with
No.
space?
So the question is, did we add an extent? This was not. We're dealing with the database just internally, so it had nothing to do with the extent. So there might have been some fixed extents, but I don't think there were. It's probably just all variable because the disk was so fast. So, but the point was, it grew a cluster, which is insignificant when you're looking at 126 gigabytes. It grew a cluster, started filling that cluster, and knew that it had all these free clusters in the back. So it just started filling up the free clusters in the back, because there was a big chunk of empty space, like 500 million rows of empty space in the front of it. So that solves the database growth. It doesn't solve it if you have interleave deletes, but if you're in a situation where you're deleting archived data, so you're deleting audit tables, history tables, and those are somewhat ordered, and you're doing a massive delete, so you have all this empty space in front of where your current space is, table reorg will not grow the database, or it shouldn't grow the database much.
But don't count on that.
Yeah. Okay.
That's going to depend on having a very well-ordered usage of the blocks initially.
Correct.
Yeah.
Yeah.
Who has a production database where that's the case?
Right. So to repeat Rob's statement for the record is that's going to depend on a well-ordered database to start with. Okay, but let's assume that we solved that problem, because it certainly felt like we solved that problem. So let's talk about the startup time. So again, that 2-hour startup time is a non-starter if you're going to be running this on a nightly basis. If you've got an 8-hour window and to go do this, and you're going to run it for 8 hours, then stop it, and 2 of those hours are spent just spinning, trying to figure out what to do. That's a pretty big problem.
All right, so
So here's is this you or me? This is still me. So here's this is from the documentation. Here's all the arguments you can have. So you can resume, you can specify the number of records, no smart scan. I tried most of these. And so this is where I say, I didn't see the option to make it so it doesn't display anything. I tried most everything here. I thought the no smart scan would have been the solution, but it wasn't. What the solution was the search depth. So the search depth was searching the chains to figure out how far down the chains and how much it can reuse. So this comes back to probably what Gus was talking about, the RM chain, that you're not supposed to be looking at the RM chain, the whole chain to find space. You're supposed to give up. And I think the search depth, this might be looking down the whole entire chain to find a spot, and the search depth limited how far it could go. By default, the search depth is 100%. It can range from 0 to 100. I set it to 5. Oh, here's what it says, right? So this is again from the documentation. Specifies the percentage of the record-free chain to search for free blocks to be used during the table reorganization. Minimum is 0, maximum is 100, and the default's 100. So
which doesn't seem like a good value.
no. Well, it took 2 hours to read through the entire RM chain, right? So so that was not the right thing to do. So we did recs at 1,000, search depth at 5, so that's 5%. And it didn't take 2 hours. It took about 2 minutes to start. Paul?
Can you go back one?
Paul?
Is the theory then that it searched 100% of the RM chain looking for an empty block because it doesn't want to insert into an RM block that has records in it already because it defeats the purpose of a table reorg?
We don't know.
I don't know, but that seems like a good theory. All we know is what the documentation says, because none of us have the source code anymore, so we can't look at it.
Yeah.
It also means then that in those earlier scenarios where your RM chain is growing, your searches get more expensive over time.
Yeah,
Right.
right. Okay,
Back one?
back to this one.
Yeah. So these are all of the various options you can have. So one of them is don't write messages to the screen. But one that occurs to me that's missing is run for 2 hours and then stop. What?
Info is the one that says don't write to the screen.
Yeah.
Okay, I didn't use that one because I thought I know the info with this.
Okay.
Right,
go.
right. So the way to stop this is you have to use ProShut, -C, disconnecting the user to get it to stop, or Control-C. But if no, or Control-C. But if assuming that this is running from batch from a cron job or a scheduled task, you have to then have a mechanism to terminate it, which is not kill 9. Okay, so here we go. We talked about this. Just for comparison's sake, before the table reorg 31,003 data clusters, a fresh dump and load was 15,499. That leaves 15,504 empty clusters, or 7 or almost 8 million blocks that had to be scanned, and that accounts for the 2 hours of time at the startup time for this. So we found the solution, which is search depth. 5% was, like I said, it was like a 2-minute scan. So this could be the solution to let this thing run periodically overnight. So let's talk about periodically overnight. So what's the oh, go ahead. Oh, time, really?
No, 5 minutes.
Okay, so what about performance impact? So I modified the ATM. 150 users, 7 of them were doing typical user update activity, what the ATM does. Goes and finds an account, changes the balance on account, changes the balance on a branch, changes the balance on a teller, and then creating a history record. So 7 of them were doing that. And then 143 were just doing reading. They would find an account, and then they would read 100 more accounts. So it'd find a random account and then do a for each to read 100 more from that point forward, and then read a telnet branch. So it was just a complete reader to try to make it so it's not a update intensive activity, because we knew that table.org was going to be update intensive activity. So the baseline with 150 users, you can see some of the metrics here about how many records were read, how many were updated, and what the longest wait time was. During table reorg, you can see that the transactions per second cut in half, but really I think the story here is look at the longest wait times. There's 146-second longest wait time. So that means that if you had a user that was doing something, they could have been waiting 146 seconds for the screen to update. So that kind of tells you that you should not be running this during the application day, because it would have significant impact on the application.
So don't run it right before lunch.
Okay, so then let's compare this to a dump and load. So again, our best case scenario was 8 hours, 40 minutes with the one that had the biggest the biggest chunk of data before that was empty. Do a binary dump and load. Binary dump and load took 43 minutes to dump this database. Load it took 24 minutes. Index rebuild took 8 minutes. So that's an hour and 15 minutes compared to 8 hours and 40 minutes, right? So certainly dump and load is going to be faster, but it has its caveats. You have to disable after imaging and re-enable after imaging, which means you need to do a backup of it in order to re-enable after imaging to get your starting point. And if you disable after imaging, you have to disable replication. So if you're running OE replication, then you need to re-baseline after you have after imaging enabled and all that stuff, where table reorg allows after imaging and OE replication to stay intact. And based on the zero downtime session I did earlier yesterday, it was asked, well, how does what we did with the table petitioning compared to reorg? So this is what I did yesterday, was ran some more benchmarks. so petitioning took, I took that small database that I did in that presentation. If you don't know what I'm talking about, there were 500,000 rows in that database. And I just did the petition move. So that is using table petitioning, setting a value from 0 to 1 for each record, and that's going to move it from one petition to another into a different storage area. That took 2 minutes, 7 seconds. Doing table reorg, it took 1 minute, 25 seconds, significantly faster. Buffer copy, so that's a question I think you asked. Compare this to buffer copy delete. That took 2 minutes exactly, and then I dumped and loaded and index rebuilt the database, and it was 46 seconds. So this is a much smaller database, but why I did this is we were a little bit surprised about the AI space that the petitioning cost. If you remember, it was a 10 gigabyte database, and it created 233 gigabytes of AI space, which was, I think, a surprise. So you can see here, here's the AI size for each one of these moves. Obviously, dump and load didn't have an AI size because you're just dumping and loading. And then here's the number of AI notes using AI image scan and grepping out RL unscore to get all the notes that it created. So you can see that partitioning created significantly more AI space than table reorg does. And then buffer copy delete creates more as well because it's through the 4GL and there's just more things that it's doing.
Question?
Yeah.
But with the table reorg, it's expected that you have a response time on the application.
With the table reorg, we saw the response time issue, which was right here, right? Where the table petitioning approach, you have control over it. You could put sleep time in it. You can restart it. There's a lot of advantages to having some control. Table reorg, you don't have any control. You start it, and the only thing you can do is stop it. It's going to go as fast as it can all the time. Something different. It's you, not this.
A homework assignment. So, turn on after imaging and run the table reorg, then do an AM and scan verbose and see what you get. I'm not going to reveal the results to you because it's a homework assignment. but I do know what it does. All right. So that's the end of our data that we've collected. What is table reorg going to do for you? Well, it's going to minimize record fragmentation, and we think, based on our results, that it's going to do a pretty good job about that. And then, as best it can, it will make the physical order match the index order. We need more experience to know how good a job it does at that. It should do a good job, but we don't have enough data from real databases to be sure. Performance after you've run it is probably going to be better. Table reorg works on a table at a time. So if you have 500 tables in your database, it's going to take a while to reorg all of them. But you probably don't need to reorg all of them, because most applications make heavy use of a few tables, and there's lots of tables that are not updated often. So pick the ones that get used the most. DB analysis will tell you how much fragmentation there is and the size of all the tables.
So it moves all the records. Beware, row IDs change. So you got to watch out for code. Code that does find first, customer no lock, and then say run update.p with rec ID customers, and it may not work well during the process of table reorg. And if you're storing row IDs, I don't think anybody's doing that anymore except for the Pro2 product. So how would the Pro2 product behave with this? I don't know the answer. I would hope that change data capture would fire, but I don't know. We'd have to experiment. Yep. Table storage area will expand. Previous record locations will be on the ARM chain, and the ARM chains became huge. So the expansion is going to depend on what the ARM chains look like.
So in conclusion, we think table reorg is obviously a useful tool to remove fragmentation and scatters if you need to do it online. It's kind of pretty fast, sort of, maybe, for varying values of fast. That Gus's opinion is it was fast.
Tom objects to me having said that.
He's like, how come I have to say this?
And the reason I said it is because when I started running it, it was going quicker than I expected. I expected it to be much slower than it is. And as you see from the comparison of the other ways to get rid of fragmentation, it beats them all. So pretty fast is an accurate assessment.
I'm pretty sure dumping and loading was quicker.
Except for the rebaseline.
Right. So, yeah. So basically, if you're in that situation where you don't want to rebaseline or you cannot rebaseline, this is kind of your only option in a lot of ways. So while you get the table partitioning, but does anybody have a table partitioning license? Okay, so a few people. But your database is going to grow, will probably grow, depending on how your free space is organized. You should certainly run it at off hours, and you're probably going to have to restart it a couple of times, so you'll need to be prepared to deal with that. You should definitely test it before you use it in production, especially if you have any production activity going on during the hours when this is happening. Those long wait times would be brutal for certain processes. It's great that it can be restarted if something goes wrong. That's a great feature. The default change for search depth for limiting the startup time is going to be important. And as always, your mileage may vary. Rooms, transportation, meals, tips, taxes, not included.
So we've been scouting locations for a future secret bunker. So this is one possibility. Now, we are out of time, but if you want to ask a question or two, we'll take them, but then we got to clear out.
Oh, it's lunch. We got plenty of time.
Oh, it's lunchtime, right. Forget it. Okay. So,
Any caveats or thoughts about that?
I'm sorry, I didn't hear the first.
Multi-tenancy database.
Multi-tenancy database.
It should work because you can do it by partition. And I have to say, the utilities have been very, very sensitive to dealing with multi-tenant and partition. Most of them account for it. So we'd have to go back to the slide that had the usage, the syntax. And I think you can specify a tenant.
Yeah, and since the multi-tenancy pretty much does the same thing as table partitioning does, it'll work for both. Of course, the names of things are different, but conceptually, it's almost the same thing.
Yeah.
In the back?
So setting the search depth really only changes your startup time, right?
Yeah.
It doesn't impact the other behaviors in terms of...
We don't know enough. So the benefit we got was it changed the startup time. So if I read in the documentation, the search depth is building a list of places that things can go, is what it sounds like. So now we're limiting that list. So there may be some downstream.
I was just thinking about adding all those blocks on the edge, right?
Right.
Yeah.
Well, and I think that's the goal, right? As Gus said at the beginning, it would be great if there was a architecture that would just append all the time and not try to reuse empty space.
Yeah,
It'd be useful.
In any case, that's a topic that requires some more detailed
Yeah.
study
Rob?
and testing.
You said that you had, with the default, you had a 2-hour startup time.
Correct.
I'm wondering, did you test the break and resume, and would it be 2 hours every time?
Yes, so that's a really good question. Rob asked, so that 2-hour startup time with default where search depth was 100, did you stop it and restart it? So did you let it get to the 2-hour period, stop it, and then restart it? And did it still have the 2-hour startup time? And the answer is yes. I did do that because I had the same hope you had, is that this was a one-off to get things set up and then it would go, and that's not the case.
Yeah. On the other hand, we didn't investigate stopping and restarting in any other scenarios other than this one.
Yeah. Mike?
It's more an ABL question. The find current statement, does it use row ID?
Will find current
Use the row ID.
using the row ID be bothered by this?
During a move, because the rec ID moves.
Yes, if you move the record, then find current's going to fail.
Is that true?
I don't know.
I would hope not.
But it,
Does find current go through a cursor? If it goes through a cursor, it's going to work.
yeah,
Okay, we can ask ABL people.
Yeah.
yeah. But I'm pretty sure it's going to go by the row ID. But I don't know 100% that that's what it does.
Right, because this is not just this. Table partitioning, multi-tenant, all those can be done online, and find current's going to cause problems in those environments too. Anytime that a row moves, right, through a utility, then it's going to have a problem.
We think.
Yeah.
But we got to ask the 4GL guys.
Yeah.
It's not really online to operational wise. I mean, if you can run it online, but if it has impacts on the ABL, whatever it does, pretty much,
Right.
Well,
be a challenge.
yes, but it's not supposed to fail.
Right.
So if it in fact does fail, then that's a bug.
You'd have to work pretty hard to catch it doing it, though.
Yeah.
Yeah.
Maybe you don't know.
Anybody else? Yeah.
How did you do the resume? Did you just restart the table reorg?
With the resume,
You did use the resume.
I did both. Because I really wanted to get rid of the 2-hour startup time. It was painful to sit there and watch it. I wrote programs to go look at the VSTs to say, tell me when a record actually moves, and then it would output it to a file to say, it finally happened, because I wasn't going to sit there for 2 hours, and it happened all the time.
See, that's what Mike does when he has to wait. He writes code.
Yeah.
Any more? No? Okay. Thank you for coming.
Yeah. See you guys next year.